Just to remind you what we did in class on Friday, we introduced a dot product in 2D defined by component-wise sum of the products of coordinates of two vectors. And we showed that the dot product has a property that A dot B is also equal to magnitude of A times the magnitude of B times cosine of theta. And from that, we discussed that one also should be able to determine cosine of the angle between two vectors simply by solving this equation with respect to cosine of theta. So this is A dot B divided by magnitude of A times magnitude of B. So today I want to talk about other applications, and I already discussed this in one of my classes, but so if you see the repetition here, this is just because I did not cover it in two of our classes. So let's talk about something called projections. And in this case, let's say that we have two vectors, A and B. And what I want to do is I want to find two things. The first thing, if you shine the light in a direction perpendicular to the vector B, and you want to find the length of the shadow of a vector A, so you want to determine the length of this segment. This is called a component of A onto B, and it's easy to see, I hope, that if the angle between A and B is theta, then the length, this comp AB can be determined simply by taking the length of A, right? This is a simple trigonometry. By taking the length of A and multiplying it by cosine of theta. But then if you look at the formula that for the dot product, you see that essentially here on the right hand side you see exactly the same thing as what you see on the right hand side here, except for the extra factor of magnitude of B. So if I take this equation and divide both sides by the magnitude of B, I'm going to recover exactly what I need. So this would be the same thing as A dot B divided by the magnitude of B. And I can also interpret this expression in the following way as A dot magnitude of B over magnitude of B, which, as you recall, is a unit vector in the direction of B. So the component of A along B, or the length of the projection of A onto B, is given by this expression here. Okay, so then the next thing that I want to do, clearly if I take a vector A, then I can always write A in the following way. I can write it as a vector along B plus another vector in a direction perpendicular to B. And my question is, can we figure out what the green vector along B is going to be? The green vector is called projection of A onto B. And let's see, so for the projection of A along B, we know already that its length is the same as comp A along B, right? So the length of this vector is known. And number two, that this vector is along a vector B, so it has the same direction as B. And so that means that I will get this projection of A on B. It's a vector with the magnitude comp AB and the direction of B, so it is the direction of a unit vector along B. So times B over magnitude of B. Right, because now if you find the magnitude of projection of A onto B, you see that the magnitude is going to be the component of A onto B times the magnitude of a unit vector, and the magnitude of a unit vector is 1. And so now if I substitute the expression for comp AB into this equation, I will have A dot B divided by the magnitude of B times B over magnitude of B, or if you wish, A dot B divided by magnitude of B squared in the denominator, but magnitude of B squared is the same thing as B dot B times a vector B. So let's do an example. Now, this, of course, again, will be true in 2D or 3D. So let's do a three-dimensional example. So let's say A is 1, 0, 2, and B is minus 1, 1, 1. And I want to find both comp A onto B. Actually, I want to find four things. Comp AB, comp BA, and then projection of A onto B, and projection of B on A. Now, I hope that you can easily see that, for example, comp AB and comp BA are not the same thing, right? Because, again, if I have two vectors like so, and I find the projection of A onto B, I'm going to get, or component of A along B, I'm going to get this length. But if I want to find projection of B onto A, I have to drop a perpendicular from the tip of B onto A, and that is going to be a totally different number, right? It's going to be this length. And the same applies to projections, right? Because projection of B onto A will have a direction of A, and projection of A onto B will have a direction of B. Okay, so let's do comp. So comp A onto B is A dot B divided by the magnitude of b. So a dot b is 1 times minus 1 plus 0 times 1 plus 2 times 1. And the magnitude of b is square root of minus 1 square plus 1 square plus 1 square. So this should be 2 minus 1, 1 on the top, and square root of 3 on the bottom. Then component of b onto a is still a dot b, but now divided by magnitude of a. So a dot b is still the same, right? It's still 1. And the magnitude of a is a square root of 1 square plus 0 square plus 2 square. So that's 1 over square root of 5. Okay, and so now we find projections. Projection of a onto b is this, or we can use that expression because we know the component of a onto b already. So either way, this is going to be a dot b divided by b dot b times b. And a dot b still hasn't changed, it's still 1. And magnitude of b, we found before, this is square root of 3, so this is, or you can just take a dot product of b with itself, that's 1 plus 1 plus 1, and times the vector b, minus 1, 1, 1. And so this is equal to, let me move this a little bit. This will be equal to minus 1 over square root of 3, 1 minus 1/3, 1/3, and 1/3. And likewise, projection of b onto a is a dot b. But now this is divided by a dot a, and this multiplies a. So a dot b is 1. Magnitude of a was square root of 5. So square root of 5 squared, 1/5. And then a is 102. And so what we get is 1/5, 0, 2/5. Okay, so this is just formulas that you can remember or reconstruct as necessary based on the pictures that we drew, and then you can just use these formulas to find the components and projections. All right. The next topic that I want to discuss is one specific application of a dot product, and that is work. So if you have some mass m and a force that acts upon this mass that moves the mass from some old position, maybe at 0, to a new position at L. And the question is, what is the work done by the force to move this block? All right, so I hope that you remember. So this is a force F. Of course, force is an object which has both magnitude and direction, so we can represent it by a vector. And the work is, according to physics, is equal to the magnitude of the force in the direction in which the object is moving times the distance by which the object has moved. So work is going to be the force times the distance. Well, in this case, it's clear that the distance is L. And what is a force? Again, I can take this force and decompose it to the sum of two components. One component along the direction of motion, and another component perpendicular to the direction of motion. Clearly, the component that is perpendicular to the direction of motion doesn't do any work at all, right? Because this is a force that acts in the direction perpendicular to the direction of motion. So what is the magnitude of the force in the direction of motion? If this angle is theta, then again, trigonometry says that to find the horizontal component, I need to take a magnitude of F and multiply it by cosine of the angle with the horizontal. So this would be my force, and the distance is L. So this is the formula, which I can actually rewrite in the following way as magnitude of the force times L times cosine of theta. And now if you think about it, this looks suspiciously like a dot product, right? Because you have two positive numbers times cosine of the angle. And it's easy to see that if I introduce a vector L in the direction of motion with a magnitude equal to little l, then what I have just got for the formula for work is nothing but vector of force dot with a vector of a displacement, right? So L is a displacement. It also has a magnitude and direction. In this case, displacement is along the horizontal line. Its magnitude is little l, and you take a dot product with the force, and that gives you work. So if you want to find work done by the force, by a force, then what you need is to take a dot product by constant force. You need to take a dot product of the force and the displacement. Let's do a quick example. So let's say a block moves at 45 degrees to the x-axis under the action of the force F with components -1, 2. If the block has moved by 2 meters, find the work done by the force F. And the point is that in this case, the only thing that I need to do, I know the vector of a force is constant, I just need to find the displacement vector. And I know that the displacement vector is 2, and I know that the displacement is in the direction of 45 degrees. It doesn't matter actually where the displacement starts, so let's start it at 0. Oops. So this is my displacement vector L. So I know that the magnitude of L is 2. And because L points at 45 degrees, then L is in the same direction as a unit vector with components cosine 45 degrees, sine of 45 degrees, or square root of 2 over 2, square root of 2 over 2. So then, as usual, if I know the unit vector in the direction of L, and I know magnitude of L, then L itself should be equal to magnitude of L times U, and that is 2 times radical of 2 over 2 radical of 2 over 2. So L is square root of 2 square root of 2. And so now work is going to be F dot L. F was minus 1, 2. And you're taking a dot product with radical of 2, which is minus square root of 2 plus 2, square root of 2, square root of 2. So that's our work. Okay. So now we're ready to discuss the next product of two vectors called cross product. And this requires some preparatory work before we can define it. What I would like to do then is to quickly review or introduce, whichever the case might be, a concept of a matrix and determinant of a matrix. So, a matrix, in fact, we don't need any matrix, let's just do a square matrix. M by M matrix is a table with M rows and M columns. So for example, something like this, 1, 2, 3, 4 is a 2 by 2 matrix, and something like this, minus 1, 1, 0, 2, minus 1, 3, 4, 2, 1. That would be a 3 by 3 matrix. What is important to us will be a concept of a determinant of the matrix. And there will be a different rule how to compute this quantity depending on the matrix size. So if matrix A with components A11, A12, A21, A22, now these are just numbers that enter into the matrix with 1, 1, 1, 2, etc. These are called indices, and they simply indicate the first index indicates a row in which a number is going to be, and the second index indicates a column. So, for instance, A21 is somebody who is in a second row in the first column. So if A is like this, then the determinant of A is going to be a number that I'm going to denote again as a table, but with straight lines instead of the parentheses. So C straight lines is a determinant, C parentheses is a matrix. So this is defined as product of elements on the diagonal, or it's called main diagonal, A11, A22, minus the product of elements on the secondary diagonal, minus A12, A21. And if A is a 3 by 3 matrix, so A11, A12, A13, A21, A22, A23, A31, A32, A33, then its determinant is defined as follows. So again, it's the same table but with the straight lines. And this is going to be computed in the following way. So you take an entry A11 and remove the first row and the first column that contain this guy. Now that leaves you with the matrix A22, A23, A32, A33. This matrix is a 2 by 2 matrix for which we already know how to compute a determinant. So what we're going to do is we're going to take A11 and multiply it by the matrix, by the determinant of a matrix that remains once you remove the first row and the first column. So A22, 23, A32, A33. And then you continue in the same vein. So you now go to a component A12. You delete the column and the row that contain this component. This leaves a 2 by 2 matrix, A21, A23, A31, A33. And again, you take a product of A12 times the determinant of a remaining 2 by 2 matrix, A21, A23, A31, A33. The strange thing here is that for A12, you're not going to put a plus in front, but you put a minus. And lastly, you look at A13, you cross out the first column, first row and the last column. Again, 2 by 2 matrix remains, and you multiply A33 by the determinant of that matrix, A21, A22, A31, A32. And here you use a plus sign in front of A33. All right, so this gives us a determinant of a 3 by 3 matrix. Well, so let's do a couple of examples. Let's say I want to find the determinant of 1, 3, minus 1, 2. That shouldn't be very difficult to do because I simply take a product of elements on the main diagonal minus a product of elements on the secondary diagonal. And so in this case, it's 2 plus 3, 5. And then actually, let's take this 3 by 3 matrix that I already wrote, and we find its determinant. Using the recipe that I just showed you, this will be the first element in the first row, minus 1, times the determinant of a 2 by 2 matrix that remains once you cross out that element, minus 1, 3, 2, 1. Then minus, right, you have to use a minus sign for the second term, minus second element in the first row, which is 1, times the determinant of what remains if you cross out the first row and the second column, 2, 3, 4, 1. And then finally plus 0, right, the last element in the first row. And then it doesn't matter what I multiply by 0, right, because the answer is still going to be 0. And so this should be minus 1 times minus 1 times 1 minus 2 times 3 minus 1 again, 2 times 1 minus 3 times 4. And that is, so in the first parenthesis, minus 1 minus 6 minus 7 times minus 1, 7. And in the second parenthesis, 2 minus 12 minus 10 times minus 1 plus 10. And so unless I made a mistake, this should be 17. Okay, so as long as you know the rule, you should be able to do this pretty easily. Okay, so let's now give a definition of a cross product. Given two vectors A and B in 3D, the cross product between A and B is defined in the following way. A cross B is equal to the determinant. The funny thing about this determinant is its first row is going to contain the basis unit vectors I, j, and k. And then components of a vector A1, and then components of a vector B, components of vector A, and the last row are components of a vector B. So now if I use the definition of the determinant to compute this, then I'll have, so I cross out the first row and the first column, and I is multiplied by A2, A3, B2, B3, then minus J, cross out the first row and the second column, A1, A3, B1, B3, and then plus K, cross out the corresponding row and a column, and you get the determinant of A1, A2, B1, B2. Now, if we compute this, then we have A2, B3 minus A3, B2i plus, okay, so A1, B3 minus A3, B1 is my determinant of my second determinant, but it's multiplied by minus sign, so if I distribute minus sign, I'm going to get A3, B1 minus A1, B3, J. And then lastly, plus A1, B2 minus A2, B1, K. So dot product of two vectors was a scalar. This guy now is a vector with components. So let's write it in components. A2, B3 minus A3, B2, A3, B1 minus A1, B3, and then A1, B2 minus A2, B1. Okay, so again, doing an example. Now, you have two choices here. You can memorize this final formula. I don't do that. I just remember the derivation. It's always easy to reconstruct what this formula is. So if I have two vectors, maybe A with components 1, minus 1, 1, B with components 0, 1, 2, then A cross B is I, J, K, 1, minus 1, 1, 0, 1, 2. And computing the determinant, that's I times minus 1, 1, 1, 2, minus J times 1, 1, 0, 2, and then plus K times 1 minus 1, 0, 1. And so that is minus 1 times 2 minus 1 minus 3 I, then minus 2j, and plus k, or minus 3, minus 2, and 1. As a last exercise, let's also compute this. So now A cross B, this is a vector. and A is a vector. So I can try to compute A cross B dot product with A. And likewise, I can try to compute A cross B dot product with B. So let's see what that is. So A cross B is minus 3 minus 2, 1. And A is 1 minus 1, 1. So this is minus 3 plus 2 plus 1. And that is 0. That's pretty good. Now A cross B dot B, minus 3 minus 2, 1, dot product with 0, 1, 2. So minus 3 times 0, so that's 0. Minus 2 times 1, minus 2, 1 times 2, 2. This is also 0. So what is the conclusion from this computation? In this case, A, because the dot product is 0, we discussed last time that means that A and A cross B are perpendicular. And dot product of B with A cross B is also 0. So that also means that B is perpendicular to A cross B. And we'll see next time that actually this is always true, that the cross product of two vectors, that's one of the reasons to introduce it. The cross product of two vectors always produces a new vector which is perpendicular to two vectors of which you have taken the cross product. All right, and we'll continue tomorrow.